Let me just start sharing and to uh, okay, hello. Yeah, okay, thanks. Yeah. So covering up from a long way of the RL. So recently we have done several new system design on the RL side. Let's go to one document and take it. Yeah. As we can see here, we've wrote a really in-detailed code walkthrough for the Virl development, and we're specifically aiming at the multi-term utility. Yeah, in the beginning, I think that we are writing a docs to read to get everyone familiar with Virl. But finally, after we done this, we figure out that these kinds of system design problems is generalized. Yeah, just as I said, any kinds of RL frameworks should considering these kinds of problems, like the placement, like the update weights, like the log probability recompute. Yeah, so we sharing the strategies the framework Virl they are using, and I think a lot of other frameworks we also see the trends like in Real, like in Slime and or in Roll. Yeah. So hope we can give a generalized uh things on these kinds of frameworks. And today I'd like to start with these documents. And actually, I won't go into every part of the document. I will just read to several parts that we have recently done. So the first part we want to discuss about is in detailed comparison between the placement algorithm. The first, as we all know, we have chiefly two placement algorithms. The first one is the disaggregated placement. That means we try to disaggregate the actor models rolling out and the actor models training into two different sorts of devices. And on the other side, we have a co-allocated, sorry, let me see. Yeah, on the other side, we have a collocated uh, placement algorithm. That means we collocate the actor models rolling out and the actor models training on the same device, and between each stage, between the sampling and the training stage, we switch these two components, and we chiefly like offloading the rolling out but uploading the training, and after the training we offload the training engine and uploads the rolling out engine. Yeah. And we can take a picture to see what I'm discussing about. Yeah. This picture shows Virl's placement algorithm. It's like they place the rolling out engine and the actor model's training on the same device, and between the training, the sampling, and this is sampling, this is making experience, and this is the training. After sampling, they offload the rolling out engine and upload the trainer, and after the training, they offload this and upload right. Yeah, and on the other side, we have a typical placement group like this one. They place the rolling out and the trainer into different devices. Yeah, and this could make us think about some things. Huh? Are there any problems? Yeah, I think it's cool. Okay, so here we have three stage, right? The first, this line we say this is sampling stage, and this line is like the making experience stage, and the final line, this line is like the training stage, and we are looping across the three stage. So the problem is that if we try to disaggregate the rolling outs and the training, it seems like a lot of the GPU computing time is being wasted. Like when you are doing rolling outs, your trainer, I mean the GPUs you use to train the model is being wasted. And on the other side, when you are doing training, the GPUs you use to rolling out is wasted. It seems like yeah, it's two-side swords, and you have to lose one even part of the GPUs when even part of the GPU's computer time, right? And and to the best of our knowledge, directly take this picture. It seems like at least for these machines, like for the collocated one, the GPU wasted time is less than the GPU than the disaggregated one. So this gives us a direct feeling like the disaggregated one may be more it's quite like a waste of computing resources. Yeah. So we see the paradigm of training from a totally collocated one to sorry, we're seeing at least for recent 2 years, we see the paradigm from the disaggregated rolling outs in OpenRTF to the collocated rolling outs into Verb. But today I'd like to make somehow emphasize, does collocation really saves a lot of the computing resources? Or on the other side, is the disaggregated one really standardized for your computing resources? I have to say that's not the case. So the first thing that the length of these stages is not unique. Sorry, is not equal. In this picture, it seems like these two stage, I mean the generation, the computing experience and the final training stage, they are the same, they take the same times. But actually that's not the case. Most of the case, our rolling out time is rather longer. So we can somehow like first we expand the generation stage, and it takes actually longer time. And on the other side, the generation, as long as the generation is takes longer time, we can imagine that people tends to use more devices. Somehow like we use more GPUs for the generation and use less GPUs for the computing experience. Yeah, and that also happens. So the thing that this picture is not accurate. So the actual time may diverge. The actual time may diverge. So this aggregate survey mean if we spend more machines on the rolling outs and the rolling out takes more time, is actually disaggregated rolling outs won't waste so much of your GPU computes. Yeah. Okay, so that's the first takeaway of today. So we should remember the picture, like the stage and the stage transfer into the RL training. But the actual time of these kinds of training is variant, right? So the rolling out actually takes longer time, and the rolling out actually takes more machines. So in this sense, disaggregated serving won't waste so much of the resources. Yeah. And the second part, uh, I think everyone has noticed that recently we have new paradigms in the asynchronous RL. There are famous papers like this one, the Llama RL, right? And it's a new paper and being cited by Wax, okay? And the real, a real stands for longer time, and I think this paper is better than the whatever. I think it should be much better than the Llama RL in my understanding. So let's take the picture of this of their paper. Yeah. So go inside here. This is the illusion from the Ariel paper. Yeah, this is the traditional synchronized RL. They call it synchronized that you have to do the active model rolling outs and the active model training in a iteratively. Like when you are doing rolling out, you cannot do the training, and after you rolling out, you can do the training, and after the training, you can start to rolling out. That's the synchronized version. But for the asynchronous version, yeah, they have a clear definition. Like when we are doing rolling outs, when we are doing training, we do not need to stop the rolling out. We can let the rolling out engine continue to rolling out, and after the training be finished, we give an abort request to the rolling out engines, and that's all the rolling out engines to stop the generation and update the weights and then continue to generate. And that's the asynchronous RL. As we can imagine, for these kinds of collocated strategy, we cannot do the asynchronous RL at least, right? Since when you are doing training, you have to stop all the generation, and when you start, and so this page is more. I mean the picture on the left side is like the collocated training, and it cannot do the synchronized one. And for this picture on the right side, they are disaggregated, and they can do the synchronized one. And in this thinking, it seems like the waste of GPU times reduce a lot for this kind of synchronized disaggregated placement, right? And remember, the rolling outs and actually takes longer time and more machines, so the picture could be higher and longer. So actually, the wasted time for the GPU compute is much less than we think before, right? So that's the second takeaway, is that the collocated placement cannot um realize the asynchronous RL. But if we can allow this kind of synchronization, into disaggregated one, it is much more quicker than we think. Yeah. And this paper revealed give a clear improvements on the actual performance of asynchronous RL. They are using a modified PPO algorithm called the decoupled PPO yeah, in this stage. I figure out that sorry, I mean, these equations have some problems inside, and I think Professor Wu, maybe he wants to make some clarification on these equations, but the paper is actually good. So I highly suggest that if you feel interested, you can go inside their system design. Yeah. Okay. So that's the first two takeaway. We discussed about the collocation and the disaggregation, and the disaggregation allows the utility of asynchronous RL. Yeah. Today we can also talk about different kinds of synchronization where we a lot of people are saying these days. Yeah, like when a field is being uh, burgeoning, there's a lot of I think there's a lot of terminology that people tend to misuse this. So when we are discussing about the synchronization, a lot of people are discussing actually the different thing. So the first synchronization we are discussing today is about the asynchronous RL. It means that when you are doing training, you do not need to stop the behavior policy from sampling. Yeah. So that's the first synchronization. We're gonna discuss about our second level synchronization later. Okay. Yeah, come back to this is we have first discussed about the placement issue. So yeah, and the second part is that if we spend several times to try to optimize the collocated placement. Remember the collocated placement is like this. Uh, the models, the Rolling-House model and the Rolling-House model and the training model is on the same GPU. Yeah. Hello. Are there any problems? Hello. Yeah. Um. I found that this figure may be misleading is that we first doing rolling out and then we do the training, but the idea is consistent. Is that we have a rolling out engine and this one is SGLang, and here we have a training engine is the FSTP, and um and obviously we cannot feed SGLang and FSTP into the same devices, so we have to offload it and upload it. If you are using H100, H200, or even B200, I think it can feed the same machine. It can actually feed these two engines into the GPU into one GPU. Yeah, so it maybe works, but the thing that for the rolling out, we actually expect rolling out to be as quick as possible, and also for the training, it is right. So we want to make bigger batch size as large as possible. So in this sense, we do not allocate them together, but we try to offload whatever or release it and upload it, and to make sure that our batch size is as big as possible. Okay, so the actual working style. Okay, so the first working style is like this is the most naive one. We have the rolling outs, and then we offload it, and then we somehow like we offload it or release it, and we release it to GPU, and then we upload the next one in the training engine. Okay, so let's go next. Uh, at least we see that if every time we have to release the whole rolling out engine and we have to rebuild a new training engine, it actually takes a long time, right? So are there anything we need to keep if we are doing offloading and uploading? Or in other terminology, what kinds of thing takes the most of times when we are actually uh, somehow like building these engines? So the actual thing that for SGLang engine, capturing the CUDA graph actually takes a much longer time in the actual building up the engine. So the direct idea is that each time we want to keep our CUDA graph, and then we offload our KV cache and then server models. And then after training, we upload the serving models and the KV cache and then do the weight updates. So the idea is that how can we keep the CUDA graph safe and then we do the KV cache and serving model offloading. That's the third part I want to discuss is the optimization we have done. We call it Torchman Saver. The idea is that we made the protection on the virtual address of KV cache and serving models. I mean, they're tensors, and each time when we release and remem allocate these tensors, their virtual machine keeps the same, but their physical machine is being reallocated by the CUDA driver. How we implement this is actually I can show you the usage. Like we use memsaver as a region, and in this with string, in this with strings, we somehow we protect this proposable tensor, and sometimes we use the memsaver to pose it. The pose means that we for this tensor, we release its physical GPU occupation to the CUDA driver, and the CUDA driver gets the GPU memory to be allocatable. Yeah, and after that we use this kind of resume. We have a function called the resume. It's like remember that the memsaver keeps the same keep the same virtual memory. Sorry, virtual address. So when we are doing resume, we use the same virtual address, but somehow we request a new physical GPUs. Sorry, we this time when we are using resume, we acquire the CUDA driver to give us new GPU, no new physical GPU place, right? So in this time, remember that each time our actual physical GPU, our physical VRAMs is being changed every time, but our virtual address is being kept. And the good thing is that we know that CUDA graph is built on the virtual address. It's somewhat like it's telling that how a computing graph is flow from each point on the virtual address. So as long as the virtual address is kept the same, our CUDA graph still works, right? So that's the idea is we keep the virtual address consistent, so we can make sure our CUDA graph is still working. So that's the thing we have done. Okay, so the first part. So take this idea. We have built a CUDA graph and we have the KV cache and serving model. Then we release the KV cache and the serving model. But remember, we kept their virtual address with our touch memsaver. And then the CUDA, even though the CUDA graph does not actually works, but it remembers the right address. And then the next time after the weights being updated, the KV cache will be flushed and the serving model's parameter is being updated, but the virtual address is actually consistent. So the CUDA graph still works. And with the CUDA graph, we can make sure that our rolling outs in small batch sizes actually works much faster. Yeah. And CUDA graph actually takes a small portion of the GPU, like 1 or 2 GB. So in this sense, everyone is happy, right? We offloaded the parameter and the KV cache. We keep the CUDA graph, and the CUDA graph makes the rolling out still fast. Yeah, so that's the I think we have done. It's actually amazing, and thanks so much for the help from Tom. Yeah, he's an independent mathematics genius in China right now. Yeah, but whatever, he loves coding, and we benefit and get so much help from him. Yeah, and that's the first stage. So the third takeaway of today, we use torch memsaver to keep the virtual address of our large tensors, and as long as the virtual address is consistent, the CUDA graph still works. So our memsaver actually saves the virtual address and makes the CUDA graph working right. But is that the end of the optimization? Yeah, definitely not. So take these lines. Yeah, during the weight updates. During the weight updates, we have kept the training models on the GPU, and we have to keep the serving models. So we have to do a weight synchronization from the training model and the serving model. Yeah, you can imagine that maybe sometimes someone may say, why couldn't we do a zero copy, like we directly change the pointer of the serving model to the training model? The best thing that the training models the parallelism strategy of the training model and the serving model may not be the same, right? So we have to do resharding. It's not a directly zero copy and change the pointer. So we have to do a resharding, and then we use CUDA IPC to, inter-process communication to somehow like we copied the training model's parameters into the serving model. Yeah. So whatever. When we are doing the ways optimization, sorry, we were doing the ways updating, we have to keep the training model and the serving model. And we have to keep the CUDA graph, since if we offload the CUDA graph, it's actually broken. So we never have a chance to offload it. But do we actually need the KV cache in this time, right? Remember, during the weight updates, the serving mode actually not doing rolling out. So the KV cache is actually not needed. And the best thing that after the training model is being released, could we expand the KV cache here? I mean, in this stage, somehow like the training model has been released, right? So could we take this part into the KV cache? The direct idea is that maybe we can, but the bad thing that we cannot. Since, as I said, the CUDA graph just remembers the virtual address of the KV cache. So if you actually expand the KV cache size, the virtual address is changed and your CUDA graph is broken. So, in the peak of the memory, if we have to if we have to put the training model and the serving model and the KV cache and this time, the KV cache cannot be expanded since we have to that's the virtual address being the same. And after the training model is being offloaded, we could not use these GPUs on the training model. It's actually a great use of you somehow like it's actually a great waste of the GPU. Uh, yeah. From our previous experience, the actual rolling out GPU we can use is less than half of the GPU totally for our H100. Yeah, it's actually a great use of the GPU. Yeah. Somehow, if we can use the full GPUs, so we can maybe use 75 gigabytes of the GPUs. Yeah. But right now we can only use 40 gigabytes GPUs. And if we twice the size of the KV cache, it's actually accelerate our rolling out to a large stage, right? So what's wrong with this? Yeah, and the thing that we in the previous implementation, we have to upload and offload the serving model parameter and then the KV cache in the same time. Yeah. It's we didn't optimize our implementation before, so we have to do this. And that's the idea coming from SGLang community members in LinkedIn. Yeah, and I think Bill is here today and whatever. So their team and him they rate a new PR to SGLang and also to the document saver. The direct idea is that we add tags to the KV cache and the serving model. So each time we only upload somehow like we resume the GP the KV the occupation of that tag. So in this sense, we can use multi-stage waking up. In the first time, we first waking up the serving model, and then we do the weight updates. And after that, the training model is being released. And right now, we wake up the KV cache. In this sense, the actual KV cache could be much larger and takes nearly all the GPUs on the on that single GPU. So that's the optimization we have done today. Sorry, recently. So that's the first takeaway today is that how we trying to use these kinds of multi-stage GPU waking up and we this to a large extent we expand the KV cache size. Yeah. And thanks so much from their work. Yeah. Okay. Okay. So that's the fourth part of today. Yeah, it's discussing about how we are optimizing this GPU usage. Yeah. Okay, take this back. Uh, let's go next. So, okay, we came back to the documents from the beginning. Okay, so something I'd like to mention today is regarding the uh, it's regarding the implementation of Virl. When I was first reading the code of Virl, I was so confused by this complicated class. The name is called actor rolling out the ref worker, and the next one is called the ray worker group. So, what's their actual definition? So I spent several days to figure out that in Virl, their design logistic that the worker and the worker group doesn't mean the same thing. The worker is the logistic worker of RL, like the actor, like the policy, like the rolling outs, like the critic. Yeah, these are the components from the theoretical RL, right? And the worker group, they are the rate somehow they are actually the someone like the resource manager in the Ray work group. So the worker group just require resources from the Ray process, and the worker group chiefly somehow they are controlling the resources, and the worker is actually doing the RL job. So in this sense, the actor rollout ref worker is means they combine the actor models training, the actor models rolling out, and the reference model into the same logistic worker. And the Ray worker group is that they are using a worker group. They are using a worker group to get resources from the Ray. So there's other workers like the critic worker. Yeah, it's clear that's the worker. That's the critic in RL, and they have like the Megatron Ray worker group. Yeah, that means that this worker group is the resource manager in the Ray when we are using Megatron. Yeah. Okay. Is a this is the definition I want to do today, but I actually do not think this kind of complicated implementation on other frameworks, especially on Slime and Unreal, and I strongly suggest that our community members, maybe you can read the codes from Slime and it will benefit your system design a lot. Yeah, I bet. Okay, so next time what's wrong? Okay, so mm, yeah, so and just
Hey,
let me check.
Yang,
Oh, hello. Hello,
can
Lily.
you, oh, sorry, can you send the link for this page?
You mean these docs?
Yeah, this stuff.
Oh, okay, sure. Let me send you to that.
Or you can share on the Zoom chat.
Okay, thanks. Yeah, I can share everything on the Zoom actually. Yeah. Okay. Let's go next. Oh, sorry. The Ross. Yeah. And let's go next. I want to clarify several things they use in Vero, and another thing is that the log props in Vero, how they are actually computing the log props. So first, let's review why we are using this kind of log props or the probability of each sequence of the token given the previous sequence. Is that we are doing the importance sampling, right? So um, in Virl, they have different name for the batch size. The first is that the train batch size. It means that how many prompts you are sending to the rolling out and doing the sampling. And the next one is the PPO mini batch size. The mini batch size is actually a word coming from the mini batch SGD. Yeah. Hello. Hey. Hello, Jada. Could you mute yourself or let me do it? Yeah. Whatever. The mini batch size is just coming from the mini batch SGD. That means on each mini batch, you are updating the weights of your model, right? And the final is the micro batch. The micro batch is coming from the gradient accumulation. It means you compute your gradient on each micro batch, but after each micro batch has make a final mini batch, it updates the weights for once. So you may go through several micro batch and then updates the weights for mini batch at once. Okay, so remember that for this and in this train batch size, we have several mini batch. So after the first mini batch, our target policy and our behavior policy. Target policy is the model being trained, and the behavior policy is the model we use to sample it, and not the same, right? So at this time, it's actually causing the problems of off policy. Yeah. So importance sampling is the is a simple methodology we use for the off policy mitigation. We just use this. Sorry, here the pi old is the sampling parameter is the sampling policies. The behavior policies probability of the action of that token on that given on the previous stream, and on the upper side is the target policies probability of the previous sequence on that token. Okay, so that's important sampling. So here we at least if we want to do important sampling, actually everyone does it. We should compute two probability. The first one is when we are doing rolling outs, the actual probability of the tokens, right? And the next thing is that when we are doing training, the probability of the target policy. Yeah, uh, as long as I know in 2 weeks before, we always use Megatron or FSTP to compute the log probability of these two parts. But the bad thing that I found one day I found that Virl they are adding a parameter called get log probs from SGLang, and that makes me really confused. So what kinds of log probability they're actually using to compute the importance sampling? And then I checked with their team is that they tried to use the log probability from SGLang, but found that it is not somehow like they turn to find maybe it's not as accurate as FSTP. So they both get log probability of the sampling parameter, of the behavior policy when they are rolling out, and then they use Megatron to recompute that log probability. Yeah, they choose to use the log probability of the recomputed one, right? So that's the design policy. Virl, but in a real, they are actually working. They're actually directly using the log probability coming back from SGLang and to do the important sampling. Yeah, and uh, I think each their choice both works, but I do not know could they switch. And I in my feeling that I think because Virl they may sometimes working on MOE models, and for MOE models maybe the log probability of rolling out the engine could be much less accurate. But for a real, since a lot of times they are working on the dense model, so they can still use the log probability of the rolling out. So that's the things I want to review today. The fifth part is what kinds of log probability we are using and why we need to use it. Yeah. So okay, let's continue. Uh, on our side, it's an obvious optimization for us in that we try to make our rolling out engines log probability as accurate as possible. But there's actually no people working on this side, and most of the times we only use the rolling out engine to guess the tokens. The log probability may not be as accurate as the Megatron, but we can make sure that the token is accurate, right? You can sample in the right token from the less accurate probability. Yeah. So that's the idea why we are still using rolling out engine to do inference. And I personally think that the log probability still has a place to improve, right? That's the fifth place. So let's come next. Are there anything I want? There's still something I want to share on the uh source code. Okay. Okay, so next part. Let me remember. Yeah. Yeah, I got send these blogs into our channel later. This is Bill's blog on how we are optimizing the mem usage in Perl. And this is a new example of torch mem saver. Yeah, it just tells everyone that the torch mem saver keep the CUDA graph and keep the virtual address, and we can release and reallocate the memories. And this one is the code walkthrough of the first part. Yeah. And the next thing is the sorry, let me follow. Yeah. Yeah, I gotta discuss this later. Okay. So let's come to the sixth part about the synchronization, about what kinds of synchronization we are actually discussing about. As I said, we have said a synchronized RL is like you allow the rolling out engine continue to roll out even when you are training. But a synchronized rolling out is not the same meaning. Okay, so the meaning of a synchronized rolling out is that the rolling out engine can be sorry, let me remember. Mm, the asynchronous engine, the asynchronous rolling out means that given a batch of requests you send to the rolling out engine, we first decouple all the each prompt from that batch into separate prompts, and we send these prompts through engine.generate and to get the answer, sorry, to get the response from the prompt, and we pass the prompts and get the state machine and use this state machine to doing tool calling. So asynchronous rolling out is specifically used in multi-turn agentic or tool usage, whatever you think about the rolling outs. When you are using tools into the rolling outs, we are proposing for the asynchronous rolling outs. The idea behind this is that if we do not detach each request from a whole batch of requests, we send that batch into the engine at once. It may sometimes save the time when we are doing rolling outs, like, right, you have larger batch size, so the rolling outs may be quicker. But after you get the whole batch results, right now maybe we have thousands of requests, right? So for these thousands of requests, we have to do a for loop and to pass the request. Since the answer of the request sometimes requires the tool calling, then you found that one request maybe use A tools and another use B tools and another does not use tool. So you send the A to the A, B to the B, and the one do not use tools, you just keep it returned, right? So in these times, if you have a large batch of requests and at one times, it's really difficult for you to actually manage or maintain the state machine of the each request. And remember, some requests may require different tools at once, and at different times they are requiring separate or a lot of the tools. So right now we are proposing a new paradigm called the asynchronous rolling out. As we did that, we try to regard each request from a large batch of requests as separately, and then we maintain the state machine for that request and to let it call tools and to do a loop generation or whatever thing. So all the implementation is on the SGLang rollout. Yeah. Remember in Virl, SGLang does not have a complicated model like the asynchronous model or the sync or the sync or sorry, SGLang does not have separate mode like the asynchronous one or the synchronous one. We only have one engine, and it will dynamically decide what kinds of rolling outs you want to do. If we are actually doing multi-turn RL with tools, we will use the synchronized one. And if we are actually using the traditional GRP or PPO, we still maintain the batch inference, right? So that's the thing we have done. Yeah. So for this clear definition, you can go to these two functions. The first one is the sorry, let me go. The first one is the yeah, for the asynchronous rolling outs, we have a function called the request level scheduling. Yeah, this one. Sorry, too many functions. Yeah, for the asynchronous one, just as I said, we detach each request separately, and for each one, we just we just let it go to the request level generation sequence. And for the one that we want to do it in the batch, we call it batch level generated sequence. So these two are optimized for different targets. And as we continue to see the tool usage getting to be more and more complicated, we are still trying to figure out how to optimize the state machines, right? Okay, so that's what part. Maybe the sixth part we want to say about the optimization of tool usage of Virl in SGLang. And I have to say, Real and Slime, they are also excellent frameworks on RL. And for Real, they have the agentic training with tools codes already, but I think they do not have the documents, and we have people to helping them to bumping them those documents out. And on the other side, we have the Slime frameworks, and Slime framework has a PR for the agentic training. Yeah, I think as long after it's been merged, we got to share with our community how their tools are actually maintained. And I strongly think that Slime and Real have much more clear codes than Virl. Yeah, and the Virl community, sorry, the Virl maintain team, they're saying they are trying to refactor the codes, but I don't know the process. Yeah, that's this part. So what's next? Okay, thanks. I have spent 40 minutes for today's talk regarding our several optimization. So let's recover. The first part is the placement problem. We discussed about the collocation and the disaggregation. We stress that maybe the collocation isn't that good, or the disaggregation may be not that worse. And the second part is that we discussed about the asynchronous RL. It's specifically used in the disaggregate one. We always keep the rolling out engine being rolling out, and after the training model has been trained, we update the weights and the body, but the rolling out engine is always working. And we also say what papers you should go to find that it is theoretically it's theoretically and empirically works good. Yeah. So these kinds of stillness in the rolling out engine's data may won't be that hurt. Okay. And the third part is that how we are doing a weight updates for the collocated strategy. The previous weight updates is like this figure. Yeah, we use Torchman Saver to keep the CUDA graph, and we then offload the cubic and the serving model, and after that we release the training model. Yeah, and the fourth part is that we make an optimization. We do a multi-stage waking up, upload the serving model and upload the serving model, update the weights, offload the training model, and upload the KB cache. And that's could make us use the GPU, use more GPU, right? On the next part, on the fifth part, we discuss about the reference rolling actor rollout reference worker and the Ray worker group in Virl about what they are designed for. Yeah, remember that the worker in Virl is the logistic RL worker, and the worker group in variable is the reworker group is actually doing the resource management. Yeah. And the sixth part of today's talk, we discuss about the log probability computing, like what kind of log probability we need and when we need to recompute it. And for each frameworks, what kind of log probability they are actually using. I have to say that in Slime, in their asynchronized design, they keep two version of the trained actors model, of the trained actors weights in the Megatron to do recompute, because we can imagine that there's data stillness in the samples, and then we have to compute it more accurately. So they have a smart strategy to recompute the local probability. I can share next time. Yeah. Okay. And the final part, we discuss about the complexity of the rolling out when we are using the multi-turn agentic tools. So the thing that we detach each request separately, and then we maintain the state machine for them separately. And after it's been rolling out, we've send this back to the engine. Okay, so that's all for the talk today. And there are seven parts, and I got to share it offline maybe next week or maybe 2 weeks later. Yeah. So all the documents I will send to yeah, you can see that all the document is actually public. So I will send this out. And thanks so much for listening today. Yeah, we still have 20 minutes left, but I will still here discuss about our things. So whatever problems you have. Thanks so much. Yeah.
Hi, Chen Yang. Can you hear me? You are muted, Chen Yang.
Yeah, sorry. Yeah. Hello.
Oh, thank you for your talk. And I want to ask that how does the R system that supported the disaggregated mode update the parameter of the inference engine? Yeah, when you use the collocated mode, you can use good RPC to send their handle between processes. But how does the disaggregate mode just use nickel or other method? Yes, that's my
Uh,
question.
Yeah, thanks. Yeah, honestly speaking, I begin with my REO systems from the API of disaggregated weight updates, so I'm familiar with this. The direct idea is that you use the Nico, right? You all gather the parameter on each TP rack, and then you send it to the rolling out, and then that rolling out do the sharding and updates the weights, and we have these kinds of APIs. And on the other side, some people use the update weights from disk. The idea is simple. After the model being trained, you save your trained model into the disk, and the Rolex engine reload the parameter into their GPU. Yeah. The second idea may think is ridiculous, right? Sometimes saving a large model onto the disk and then reload it maybe takes a lot of times. But things are getting changed. The first that I heard from some community member that they have better SSD that reads and writes really quick, much quicker than I expected, and I don't know why. And the next thing that there's a PR that sent to us to use multi-thread weight loading from the SSD. Sorry, I'm not familiar with these kinds of disks read and write, but their actually reading speed is much quicker than previously, 10 times better, or even at least 7 times better. So on the first side, the Nico one, you have to build a process group, and inside that process group, you broadcast and shard the parameters and updates. And on the second side, you just write it to disk and load it. So the first one, it seems quicker, and there's place and you can optimize this, right? You can make it into zero redundancy. But if we if we found out that the rolling out takes really long times, and this time people tend to adding more GPUs for the rolling outs. So it's really hard for us to break down that process group and initialize a new one and add a new worker inside it, right? So the update ways from this first is easy to implement, and the next thing is that it's much easier for we to scale up the rolling outs, right? So these are two So these are two functions, and I think they have their own they have their own strengths. Yeah, that's it.
Yeah, thank you.
Okay. Thanks. So are there anything left?
Hi, Jane. Can you hear me?
Yeah. Hey, hello.
Yeah. Thank you for your talk, and I think I learned a lot. I still have a question about the log probability stuff that you mentioned. If you roll out, it has different precision compared to the Megatron, right? They
Yeah.
recompute it. So, can you briefly introduce like why is that the case? Because if we use engine, we use like a B flow 16 execute and for Megatron they have like a higher precision that leads to better log probability because from yeah, that's my question.
Okay. So, uh, I can answer from several levels. The first thing that if you use somehow like BF16 rather than FP8, the log probability may be more accurate on, yeah, the rolling out engine's log probability could improve a lot. Yeah, that's the thing. But the Megatron still is accurate. And why Megatron is more accurate than rolling out? The direct answer is that from the kernel side, you're rolling out kernel and your Megatron's forwarding kernels are actually not the same. You have different kernel dispatch algorithms, and for all these kinds of low-level kernels or whatever saying, it's actually layer by layers, your log probability gets to be less accurate than Megatron. So that's the answer. Yeah.
All right, thank you. Got it.
So yeah, it's also you can use Megatron's forwarding to do rolling outs also, right? But that's really slow. So the rolling outs engine use separate inference engine like SGLang, and the training still use Megatron. Yeah, I think that's the crock. That's the most correct paradigm right now. And we strongly want to move forward to use rolling out engines log probability directly. And that said, in these kinds of asynchronous RL, your rolling out trajectory has data stillness. Maybe the first part is coming from the version 1 of the policy, and the second part is the version 2, and the final part is the version 3. So you can imagine if you want to do recomputation of these kinds of log probabilities accurately, it's actually hard. So each time you have to send your request to Megatron, and Megatron do the recomputation, but send it back, not used, right? So these kinds of send it to Megatron and send it back is actually complicated for current systems. And on the other side, if you do not want your request sending to Megatron be sent back, you should send you maybe we just want to send it once. So if there's data stillness, maybe some parts of the percentage of the sampling, of the trajectory is on the previous version, and only the last part is on the current policy. So in Slime, they did the smart design is that they kept two version of the parameter. The first parameter is the previous version, maybe the t minus one version, and the next version is the t times version. So they use the t version, the final version, to compute the final part of the rolling outs, and they assume that all the previous rolling outs parts is being rolling out by the t minus one. This may not be accurate, but they are use this methodology to recompute the local probability, and they actually figure out it works, right? So how to get accurate local probability? There are several things we can do. Yeah, you can both improve it on the rolling out side and also improve it on the training side. Yeah. So that's the idea. So that's how we are working on the important sampling to get as accurate as possible. Okay. Thanks. Are there any more questions?
So I have a quick question. And so in your code, I saw there's some like a mini batch and a macro batch. What's the difference on these two? Do you know?
Yeah, thanks. Just as I explained, I can put it more clearly. So the train batch size is how many prompts you send to the rolling outs to let it doing sampling. And the mini batch size is that how many trajectories in a batch you want to update your model, remember that the mini batch size comes from the mini batch SGD. In mini batch SGD, until you have a mini batch of data, then you're doing 1 times wait updates, right? And the micro batch is that how many prompts you want to use for a gradient compute. So if you compute the gradient, you may not update the weight. You may not update the weights, right? So you compute the gradient several times and accumulate all the gradients, and until it's reach the mini batch, then you're doing 1 times the weight updates. So mini batch, so the gradient accumulation, first it saves computing resources, and next it can also reach a higher mini batch, and to make sure that our batch size is actually large. And a lot of people tend to use large batch size since make the training stable and whatever thing. Yeah. So that's the difference between the mini batch and micro batch and the train batch. And in Verb, they have a complicated parameter called the real train batch size. I highly hate this parameter. The real train batch size is the train batch size times the sampling parameter of n. Since in GRPO we have the n parameters, we sample one request for several times for the n times, right? So the real train batch size is train batch size times n. So there's four batch size. Yeah. So it's quite complicated. Whatever. Okay.
Yeah, thank you.
Okay. Thanks. Okay. Are there any more questions? Okay. If there's no more question, we got to. If there's no more question, we got to stop. Maybe right now. And thanks so much for listening. And if there's anyone in the Bay Area, welcome to our offline talk. Yeah. And also, I think SGLang community will have a meetup maybe in next month or whatever. So, yeah, looking forward to it. Thanks so much for you to join. Yeah.
Thank you. Bye.
Bye bye.